Okay. So I recall yesterday, and we talked about different concepts. Um, so want to discuss more in detail the boundaries of agent, and left adjoint. Its left adjoint, uh, we call boundary tree. To do this, I'm gonna have to introduce the Whittaker category. Whittaker category on the atom. And so this is a basically a locally defined categories. It's going to look over the Ron space, and essentially the uniformization of quantity by the atom onion is what's going to allow us to define the quotation of quantity using with. So we begin by introducing the local category. Okay. So recall we have the atom versus onion for all points on space. So this is basically loops into G at the point X, modulo parts into G at the point X. Also, we have the Avogadro for G over the whole round space. So I'll probably consider both of them sort of at different times. The main feature that the Avogadro has that allows us to define the Whittaker category. So is that the loop group at X acts on the avenue. So in particular, we can restrict this action to get an action of loops of the unipotent radical of Borel. Sure. And it's the unipotent radical of Borel. Yes. And so this is basically what's going to allow us to define the Whittaker category. And so to do that, let me first say, the group that'll essentially be a category of leaves on the ethno-Osmanian, which are twisted equivariant against the character for the group Ln X emits a current. And so I'll write it over here carefully. Pi activates as well. We have the loop group, and you can project n onto its delimitation. So you have loop group modulo commutator. There's a loop group of n modulo its commutator. But now this is a product of additive groups. We have a product of loop groups, the additive groups, where the index is over. This is vertices of the vacant diagram. And now, what can we do if we have to loop group with the additive group? Well, we can take residues. You can take residues. So these are just Laurent series, essentially. So you can take residues, and that'll take you to a product of just the additive groups. And then, well, pick some favorite character of a product of additive groups, which is non-trivial on each factor. So for example, you can just sum up all the coordinates. So the character non-trivial on each coordinate. The coordinates here correspond to vertices of the thing like that. And so the composition here is what I'm calling pi. So I should say, remark, I'm suppressing twists here. So, I mean, in order to talk about residues, one would like to choose a coordinate to be able to do this, but there's a canonical way to do this by introducing some twists, the same way that, or similarly to how Standard did yesterday. But okay.
This stage was still by work with and like if I don't work with this unicorn predictor, I just work indirectly.
What would, if you don't work with n?
Yeah, by work indirectly and do this construction. So
Oh, no, because you don't have this as a product of adding. So I'm really using the fact that n is the uniform radical. Okay. Oh. So let me just say the way that you define, I'm going to define 3 of G, so which is going to be the Whittaker category on the Hamiltonian, and maybe I'll say as a form of X of Ron, we take B modules on the Hamiltonian at the form X. I don't remember if we're using B module B. B modules, and we want to impose implicit equivariance against phi. So roughly what it means, so objects which we keep are B modules on X plus nice morphism. So we call act. So act is going to be the action map from the loop group of n. on the activist climbing. And if we pull back, so P modules C, let's say, if we pull back P along the action map, one isomorphism between C and the outer tensor product of I upper 3 of the exponential movement. So I have this map here. I have the exponential E module living over GA. This was introduced yesterday. And I can pull back along this. And I can ask that I put the invariance. So the point is that pi is the character of particular homomorphism. Exponential E module is a character sheet on GA. So this is a character sheet on group of n. And so we can impose. So the subtlety here is that the loop group of n is not just an ordinary algebraic group, it's a here's the subtlety. What is character sheet? Oh. So character sheet. So if I have the group H, okay, I have its multiplication. I can basically ask, so I have some heat that I can pull back on the multiplication map. And I want to ask that I have an isomorphism. We can pull back of that, the other part of the thing itself. And of course, which satisfies the so forth. The point is though that if you have something like a unipotent group, so let me ignore the fact that this is infinite dimensional, but if I have a unipotent group in it as a space, it's isomorphic to an atom space as a spoon. And so that means that it's essentially contractible. And so what I'll get is that if I impose a covariance for such a unipotent group, then this just becomes a property rather than you Sorry? Yeah, covariance. Covariance is a property for unipotent. The reason for that is that it's essentially contractible, so that means that's pulled back along the action map. The projection map is fully capable.
So what's the high exponential
Pi upper 3 of the exponential. So pi is the map from the loop group of n. And I should be putting some x everywhere. And an exponential demodulo and here. And I can put that.
Just to clarify, are you saying that the subcategory of the modules on the money?
Sorry,
Are you saying that it's a subcategory of the modules? Yeah.
it will be, yes. But let me just say there is something subtle about defining this thing because the loop group of n is not an algebraic group. And so it's a little subtle to define the modules on it. So what you do is you can write Ln as so basically a union of subgroup schemes where the translation maps are homomorphism. So for example, the loop group of G of a reductive group is it's not an in group scheme, but it is a group in scheme. But if you take a unipotent group and you take loops, then it is an nth group scheme. Kind of. Here's the correct order, but in any case, and so really what you're supposed to do is you're supposed to impose equivariance for the restriction of against the restriction of chi. So you consider C modules on the Applicant-Riemannian, which are equivariant against this character for n alpha for every alpha. And then the point is that whenever you have the transition over there, there's a forgetful map. And so you can take the limit of all these categories and you'll reconstruct the Whittaker category. What precise definition is
I am not the algebraic group.
yes, us algebraic groups. No, they're group E. Yes.
Okay.
Okay. E X. All these. Pi, or I'm using notation just denoting pi the restriction alpha. Okay.
Yes, you could say that green maps are fully faithful. In fact, each of these guys has a full subcategory such as green modules. This limit is just the intersection of the one.
Yes, this is true. So yes, so the as I was saying before, these n alphas are intractable, and so the forgetful functor, for example, well, each one of them admits a full forgetful functor down to your gx, for example. So each one of these is going to be fully faithful, but in particular, the full forgetful functor down to your gx is fully faithful. And so you can just compute this limit by just taking the intersection inside E or G. Okay, so the fact that all of these are fully faithful, well, of course, the Whittaker category is just the intersection of these inside of E or G. So in particular, there's an inclusion map, which I'll also call the forgetful functor, which we G into D or G point X, which is fully faithful. And so it admits a say non-continuous, so it doesn't necessarily commute with full limits. Right adjoint here. Which I'll denote by star averaging, or loop group of n against the K. Okay.
How important is defining this ties to for this one?
It's not important. I mean, well, the only thing that I want, that I require here is that it's non-trivial on each coordinate. So that's actually a good point though, because I should say remark. The category which streak of G does not depend on the choice of pi. So as long as it's non-degenerate. The point is that any two characters will differ by the action of the torus. And so there's a canonical equivalent for any choice pi. There's a variant of width. So we'll call it width of star. And instead of imposing equivariance, what we're going to do is we're going to take covariance. Covariance against the character pi. So again, yeah. Yes. Okay. So with star, so instead of imposing equivariance against the loop group for chi, what I'm going to do is impose or take co-invariance. So I can do a similar procedure to one I did over here, except now I'm going to get a co-limit over here, and instead of getting a subcategory of Bristolian, get a projection map. So which projection from d grid gx to width. So it turns out, however, that these two categories are indeed equivalent. So which treat G X. So there exists a functor theta which treat sorry, yeah. Which is an equivalence.
So just maybe one remark that, I mean, there's obvious conflict when we streak to its star, namely in that we streak to in fact have to project. But that conflict is zero.
Yeah, that functor is zero. Yeah.
Unlike the case of dimensionally
Right.
uniform group. Like in dimensionality, we make that conflict zero, but it's pretty fun for the other thing.
Yeah.
Sorry, I didn't quite get, wait.
Oh, with stars. So for say an algebraic group, you can impose, well, invariances you take, so if I ignore the chi just for a second, variances I take functors from vect with the trivial action of the category of p modules on the group into the category, and the covariance is I tensor up. And so what I'm saying here is instead of considering invariance as I did with tree, I want to consider covariance. So you can imagine that what I do is I consider covariance for every alpha, so this is some the tensor up, and then there's transition functors, and I can take a covariance. And I get a projection. So invariance includes into DGRG, covariance projects. What Dennis was saying is that there's an obvious map from which tree that you just include in here, and star, and that functor is 0. However, there is an equivalence with tree.
By the way, is there an analog of this, like a dual of this, tree into the direct category being fully faithful? There's a module from the P of stuff. No, this one out here.
Well, please repeat it.
Sorry, so the question was, is this projection, for example, is projection a localization?
It's a
Yes.
very excellent.
Really, yeah. Thank you.
Or is it in the bigger interpoint
Yeah, so that's a good question. So yeah, no. So this functor here is continuous. But as I said before, averaging is not continuous. So, but there is a functor which is sort of renormalized averaging. So I can act by a certain sheet here, and I can put forward along that, and I get some functor which is not averaging, but it's some renormalized version of that, and that will match up with the projection. Okay, so let me say some basic things about structure of width. D, and then also make contact with language. To do that, I first want to recall some basic facts about dimensional complexity. So now so yesterday there was this local packet stack introduced. And we considered E modules on the local packet stack. We can call this community at X. We call this spherical category at X. Although person who will talk about derived talking will want to renormalize this category, but I don't want to ignore that. For us, we can make much of a difference. So technically, the renormalize, and the way that you renormalize, I'll just say, is this. Well, this is the E module from the optical Swannian X, just to remind you, where we impose equivariance against the arc group. So this has a forgetful functor to E module from the optical Swannian, and we can ask, we can declare an object to be compact whenever its image under the forgetful functor. Category one. Now the main thing the waves Sataki functor is a monoidal functor from check at the point X. So remember theme I yesterday introduced P check over Ron into so the point is that here this think of this as two modules on the loop group of P at X, quotient from left and right for the entire group. And so since this is double quotient, we can consider monoidal structure on this category of P modules going by function. So that's the monoidal structure that I'm referring to when I said it is monoidal functor. So just a couple things to say about this functor. So where does it take, for example, we can consider, representation. So I'm just saying at a single point, so I can consider a representation of highest weight and straight lambda. And this will go to the IC sheet on Gergy lambda bar. So here Gergy lambda bar is the closure of the orbit L plus G through T lambda. So there's T is some uniformizer on the disk, and I can consider a distinguished point of the Affen-Grassmannian, and I can act on that point. I can take the closure of that and consider its IC sheet, and that is object this representation of highest weight and those of both. So this means whenever the spherical category of G acts on some category, I also get an action of rep G check just by restricting along the
Okay, I see.
right?
Could you just say a comment from what I see?
Oh, sorry, yeah. So the Affen-Grassmannian is not a scheme, but it's a int-projected scheme. So what that means is you can consider a perverse T structure on its category of P modules. And if you consider the perverse T structure, then whenever you have some locally closed subspace of the Affen-Grassmannian, and you have some object lying in the heart of that T structure on that locally closed subspace, you can consider its intermediate extension. And so what I'm saying here is you can take the constant sheaf on this orbit. You can take the intermediate extension of the constant sheaf, and that will leave the but the thing is, because so there's no IC sheaf of the Affen-Grassmannian because there's no there's no open cell. Okay, so in particular, this gives us an action of rep check X on the Whittaker category. So the point is that this Whittaker category is, you can imagine you take the Whittaker category not of the Afton-Grismanian, but of the loop group E. And the Whittaker category is L plus G invariance in the Whittaker category of the loop group. Now the point is that the loop group acts on this category here. And so that means that the spherical category, when I mean this category here, I mean the Whittaker category of the loop group. And so that means that the spherical category will act on L plus G invariance inside this Whittaker category. And I can restrict that just through nice calculate to get an action. Okay. Okay, so goal. Okay, so inside the Whittaker category, there's a distinguished object, which we'll call vacuum of the object. And what this is I can consider, well,
Actually, Andreas.
Yeah.
Okay, I have the following very deep question. So this abstracted computing makes the United States for the first time in GMs. What is all this gravity check? Let's say it was with or whatever.
for GM.
For GM.
Well, for GM, there's no N.
Right.
So
And this is a true statement.
is what a true statement?
I mean, can you spell this out for GM just to show people like to get some feeling?
Yeah, sure. So let's see. Well, the Afton-Grismanian for GM is, I mean, so we want to consider D modules on the Afton-Grismanian for GM. So from the perspective of D modules, the Afton-Grismanian GM is just the lattice, the co-wave lattice. Sorry, for GM, yeah. For a torus, it's the co-wave lattice. For GM Z. And so these IC sheaves will just be delta sheaves at each point. And let's see. Is there something else we want to do?
Rep to check.
Oh, ref. Oh,
I guess the check is also GM representation, GM part.
well, representations of GM are just sheaves on the modules. But I mean, so you consider the functor. So the spherical category itself will differ from D modules under GM, just by the action of some algebra. But Nair-Satake actually defines an equivalence between FGM onto D modules on GM. Because D modules under GM, I mean, it's just sheaves on Z, so it's just, infinitely many copies of vect, and that's what rep GM is as well. Yeah. Okay.
Could you repeat the action of the spherical GX on the Whittaker?
Sorry?
Could you repeat the action of the spherical X category of the weight?
Yeah. So, okay, so the point is, if you have an action of the loop group itself, on some category, and you can restrict that action to an action of arcs rather than loop groups. If you can impose invariance for the action of arcs, and if you impose invariance for the action of arcs, you can ask what acts on category of invariance. And the answer is that what acts on the category of invariance will be the spherical category. Yeah. So the point is that write Witt on the Apple-Grismanian as arc group invariance for some category on which the loop group acts. Therefore, the spherical category acts as well. Yes?
Is it clear why the loop group is supposed to act on width?
Yeah, so the claim is that
The claim that the action of the loop group on B mod on G restricts the width?
wait, am I saying something wrong?
Andreas, just write the formula like LG mod L inside.
Oh, sorry. Yeah. So this is I'm saying that the loop group is acting on the right here, and I'm imposing equivariance against for the Whittaker equivariance on the left. So those two actions don't see each other.
Can I just repeat my request?
Yes, sorry.
Put the formula LG mod L inside or somewhere.
So I'm considering, so Sam is saying that what it means is you can just take D modules essentially on the loop group modulo Ln Sam's inside it.
The L there is not superfluous. Width star LG is not width star G. And now you're, okay, I'm happy now.
Yeah.
No, wait a second, so this is the width of the entire G, so width of the Grismanian is, you have also helps us in the right.
Yeah. So I'm saying, so width on LG is I impose Whittaker equivariance on the left, and this has an action of the loop group on the right. So I can impose arc group invariance. When I impose arc group invariance, I get Whittaker.
Can I ask a question about the formula? So the formula involves an action of Ln on LG that involves a die, but is that enough of groups, or is that out of the formula you were like twisting in some way, you're twisting by D modulo?
Well, yeah, you mean what does this quotient mean?
The formula.
Yeah, so by this quotient, I just mean what I said earlier.
Oh,
This, yeah.
so that's not.
Yeah, this is not a real geometric
Okay.
construction.
Yeah.
Yeah.
There is a statement. There's some twisted B mod LG mod L.
Oh,
There is
sure.
a statement there.
Okay.
Can I have one more question? So you mentioned that this is naive geometric syntopy, which gets representations of B check. But it was mentioned yesterday that if you derive, if everything is derived, this spherical Hackey category is not representations of B check, but it's everything something derived. So does that show up here?
This is not. I'm not sure who's going to talk about this, but it's not relevant for us. Yeah. So So the point is that. So the way that this functor is defined is you consider the heart of spherical category in the perverse T structure, and you construct a fiber functor. And so what you do is you get an equivalence between the heart and the heart of rep T check, and then you can derive this functor. But even though on hearts it's an equivalence, the derived functor is not going to be an equivalence. So you can then ask what this is derivatively, and the answer is that you have to add the action of an algebra.
So the question was different. So again, so here we use naive society because of the conflict of reality check. So the Whittaker category defined as one. We do this, but then you can ask the question. So derived society, what does that produce for you? It does act in the Whittaker category. It's funny and there is very clear interpretation, and we'll talk about it a little bit later, even today.
Great. Okay. So what I can do is I want to construct some distinguished object, the vacuum Whittaker object in lit tree. And so what I can do is I can consider the closed subspace here and X inside here G. So just the Hamiltonian for N rather than for G. And so I can consider it. So this also has an action of the loop group of N. I can consider its Whittaker category, and there's this there's a distinguished object in the Whittaker category here. Namely, you take the dualizing sheaf and you tensor with pi upper star the exponential, where this actually, well, this still admits a map to VA, just because the character is trivial on the R proof. There's no resonance. And so then I can star extend this to get an object that would have very on the object responding. A remark, this extension is clean in the sense that, well, it admits map from the Shriek extension. So the Shriek extension, the star extension, that's a nice thing. So the map from the Shriek extension to the star extension, that's liquid. So I could have either Shriek extended or star extended, and that's the object that I'll call back with. Okay. So now I have an action of the spherical category on with 3. So I want to consider the following.
Question.
Yeah. Oh, sorry.
So is it true that this vacuum element is the averaging of like something like delta function, the percent?
Well, yes.
It's the Shriek average, yes. So the Shriek average into the delta function. Exactly due to this remark. The Shriek average equal to the life.
Thank you.
Is there some simple explanation for the schemas?
Again, it's very simple explanation. Basically, kind of to look at orbits in the closure of this one, need orbits that don't support any particular object. So the stabilizer such that the characters don't feel the stabilizer in every point there. So the claim is map the code for the map of feet to star is 0. The reason is that the code is supported from the orbits in the closure, but most all objects there are 0. That's the one.
And this can it's slightly related with then, as you said, there's a function predicate analog of its safety, you just copy the proof for it.
If I would no function, that's yeah,
Yeah.
Another question.
Yeah.
How does this dualizing sheaf works?
Dualizing sheaf?
Like, I don't know, for n, when n is equal to jp,
Uh-huh.
the Ranger's name is very infinite dimensional. For n.
Yeah, I mean we have a map from your end to a point, we just pull
I
back.
think it's like an infinite dimensional.
Well, it's a great question. So sure, it's an in scheme. So it's a union, rising union of
Okay.
so
So I don't think a formal.
yeah, it's the coordinate. Funny thing is that it's cohomologically 0. It's one of those guys, like if you take the dualizing sheet of each kind of piece, it lives like so imagine it's kind of well, these guys are actually smooth. Take something in the dimension and it lives cohomological degree negative to n. And it passes the equilibrium with cohomological degree negative infinity.
Yes.
So cohomologically 0, yes. This category is such that the two charts. So like this category is wildly compatible with the T structure of the Flanders mountain. On the Flanders mountain itself, its structure is not separated again. The R, like with the line sheet, is not zero yet, it's chronologically zero. So the reason like people didn't discover it like 50 years ago is that we were afraid things are not visible chronologically. So it's one of those phenomena. It's a non-trivial category, yet you cannot see from the point from the Venus stuff. All the objects with the category with chronological negativity. But they exist. I see. Dark now.
Okay, so I have 3 minutes left, so you want to click through everything. So I add the function, which is I can compose the supply chain. With the action on the vacuum Whittaker objects. And the theorem will angle Roman and then Sam overrun. So these guys did it over a point. And so the factorized we overrun is that this composition here, so composition is an equivalence. And its inverse is called called the Castellan-Chalica CSGS, so it's called ELC. So the point is that you have, the Avogadro quantity is stratified by the orbits. There's a loop group of the unipotent radical, and each one of those you can take orbits through, for example, dominant co-weights, and if you take, the basic Whittaker objects on those orbits, and you can cleanly extend them, and those will be the objects corresponding for a physical complexity. Okay, so let me, in the last few minutes, quickly say the coefficient and Poincare functions. So the point is that so I can forget the trivialization, and I get that here the x on the which I'll call I x, and so this gives us a pullback functor at hypertrophy from d modulus 1 over g to d modulus x. And so now I can compose with Whittaker averaging. A functor to the Whittaker category as x, and the composition is what I'll call coefficient functor sub x.
But there's a subtle here, so the averaging is not continuous, but
it's yeah, okay, so it's
way you have to justify why it's
sure. Okay, so the point is that you can write this averaging as a limit of averaging functors for these n alphas. And the point is that, I could replace, for example, the Whittaker category with twisted equivariance against one of these n alphas. Their averaging is continuous. And the point is that for large enough objects in this, so I have this Ln is this filtered union of all these n alphas. For large enough alpha, the composition of upper streak and then averaging for that alpha, so the transition maps are equivalences. So that means that instead of just averaging for all of Ln, I could have just averaged for one big enough object in this filtered union. I can pick some alpha large enough such that averaging, averaging is all that I need. Okay, so I didn't write anything because I only have until 10, right? Sorry? Exactly, yeah.
But I thought in the remaining state for every object, you think we work with alpha to like you can just do an average over alpha.
No, I'm saying, so instead of considering the Whittaker category here, I can consider twisted equivariance for some one of these n alphas. And the point is that there's a transition functor between, whenever there's a transition between some n alpha to some n beta, there's a transition functor from pi upper streak followed by averaging for n alpha to pi upper streak followed by averaging for n beta. And the point is that when you're high up enough in this union, these transition functors are equivalences. So you can just basically define the coefficient functor to be that composition. That composition is continuous because for every pocket.
People tend to work out the last association at home. The key phrase is remember.
Yeah, good.
Let me just again, so repeat what Andreas said. So this transition, this Nash transformation is quite equivalent is when evaluated on the essential image of the conflict pi per sheet. They're not equivalent, they are equivalent when you pre-compose with pi per sheet. And the reasons for that, with remember what we'll see is the following. Then notice tan alpha and beta. The point is that if you take the subgroup in Ln and alpha times loops on the curve that's the entire curve you would call it x. So you call this group n out. So n out times n alpha is all of Ln, and alpha is large enough. This is the assertion which is responsible for this stabilization.
Great, thank you. So what should yeah, so there's also this coefficient at x, but there's also this absolute coefficient functor that I should define, which say I mentioned yesterday, which goes from D modules on G to vec, and it's this followed by taking the fiber at the origin. And the point is that this is actually independent of the choice of the point x because of something called the unital structure. I think someone else will talk about this. The unital factorization category, which means that it's functorial under exclusions of subsets of Ron. So if I have some larger subset of Ron, I get functor from here to with x prime, and that's essentially what gives me the functor of coefficient sub x followed by 2.5 where the origin of the affine Gaussian is independent of the choice. So now let me say what the Poincare is. So the Poincare for x admits in left and right. Called Poincare of x. And so what is this left adjoint? Well, I can first consider the affine Gaussian. And there's a partially defined left adjoint to Whittaker street. I lower star, and this is only partially defined. But the claim is that if I actually restrict the Whittaker category, it is defined. And the reason for this is the following. But defined on so the reason that this is defined is so the observation is that if pi over 3 is defined, then so is pi lower 3 of S star F, where S is some spherical object. But the reason for this is that there's the convolution diagram defining the action of the spherical category on the affine Gaussian is proper. And so you can see that this is defined. But now the point is that well, that's observation 1, and then observation 2 is yeah, so this will actually be S star. So, and the second observation is that lower sheet of the vacuum width is defined. The reason for this is that it's the streak extension of something in polynomic, and therefore is in polynomic, and lower streak is always defined in the category of in polynomic modules. Now, Shalika says that this composition is an equivalence. In particular, I mean, what is this composition? It's just nice pocket followed by acting on the vacuum. So that means that every object in the Whittaker category is to be expressed as the vacuum acted on by some spherical heat. And therefore, it's defined on the whole category of Whittaker objects. And that is so defined on width streak, and that's what I'm calling. We should stop there.
All right.